So solution to a system. To be a solution to the system, it has to work in not just one of the equations, but all of the equations, however there may be. They have to work in all of them. So two variables, an ordered pair of real numbers, that is a solution of each equation. And then we have solved the system of equations when we have found all of its solutions. You'll remember graphically, what we're doing is we're trying to find where do they intersect. Where's the point or points that they hit each other. So the first method that we had for our objective was using the substitution method, and my hope is that just hearing that name has helped you to remember how to do this. Do you remember how to use substitution to solve a system? What do you do? So, exactly. The obvious choice here would be we have this y. Now it's a negative y, so we'd have to do a little bit of work, but we'd try to get this y all by itself. So we'd subtract 2x from both sides, and then divide by -1, or just change all the signs, and get y equals 2x minus 10. And Cassie was loudest when she said, well, you just plug it into the other one. That's what we do. So good job, Cassie. Let's put this up in here, and let's see what happens. So 3x plus 2 times 2x minus 10 equals 1. Well, that'll be 3x plus 4x minus 20 equals 1. 7x, if we add 20 to both sides, gives us 21, which comes out to be a very lovely 3. So we get a nice integer here. I'm definitely not going to tell you that every answer you get in the homework is going to be a fabulous number, but this is a nice one. We get a nice integer. Now, we've got x equals 3. Are we done? What else do we need? Yeah, we have to find y because we need an ordered pair. Well, the good news is, by solving for y here, we have ourselves a very nice equation to just substitute this 3 back into and find it. So 2 times 3 will be 6, and 6 minus 10 is going to be -4. So we do need to write this as an ordered pair when we're done. And that's because that connects it all to the visual, which is, hey, I didn't just understand what I found. What I found is the visual of they're going to hit each other at the point 3, -4. Now, we have this y equals 2x minus 10. That's in that y equals mx plus b format. We can go ahead and graph that one. So where would this one start? -10. Okay, that is really hard to see. Can you guys even see the numbers on yours?
It goes down to -5.
Okay, so it is going, it is going down by 1s at each point here. So then we think, okay, well, how could we take care of that? Well, you could go ahead and put some numbers in, find a couple of points that'll work here. So if we want to be able to graph it on there, maybe we put a 2 in and say, well, 2 times 2 is 4, and 4 minus 10 would give me -6. That's a little bit closer to the numbers that I have on here. Maybe I'll just put that one on there. And maybe something like put a 0 in and see what you get. 2 times 0 is 0. 0 minus 10 is -10. We already knew that because that's the y-intercept. How about a 5? 2 times 5 is 10. 10 minus 10 is 0. So it's looking like that. Now we have to try and draw a straight line. I have a ruler up here, but maybe I'm not even going to cheat because you guys can't cheat. Just try to make that as straight as possible because we're hoping this intersects where we said it was going to intersect. And then we have 3x plus 2y equals 1. So again, we could get it in that y equals mx plus b format. So we'd subtract the 3x from both sides and then divide by 2. So we'll have -3/2 x plus 1/2. So we have fractions here, but it's not that big a deal. We start up here at 1/2. And then where do we go with that -3/2? Down 3 and over 2. I didn't use a ruler, but it's really not that far off. I mean, for having to just try and make it as straight as possible, it's not that far off, so we can see that. But let's just say we goof up graphing. We're pretty sure that our 3, -4 is supposed to work. What's another way that we could check this? Another way that we could check besides graphing. Plug them in. Gotta work in both. They have to. If they work in both, then they're a solution. So if we put our 3, -4 in here, we have to get 10. 6 minus a -4, yep, it works. 3 times 3 is 9, 2 times 4 is -8, 9 plus -8 is 1. Yeah, it's our solution. So a lot of different ways to represent, hey, this works. Whether or not it's just by algebraic checking or seeing the visual over here, or looking at the math that we did and making sure that everything works the way that it is. So just on substitution, 4, 3, 2, 1, 0, how do you feel about it? I just gave you some substitution problems and said, here we're going to count this for something. Good, good. So most people are remembering everything from the past and maybe just need a little reminder. This one, getting a little tougher. It says, solve a nonlinear system by substitution. Find the dimensions of a rectangular garden that has a perimeter of 100 feet and an area of 300 square feet. I don't know about you, but the first thing I'm doing is a visual. I know rectangles by definition from geometry have 4 90-degree angles. Tell me something else that might be helpful about rectangles. Opposite sides? Congruent? Okay. So I don't know what they are, but I could sure grab a couple of variables and say, well, those would both be x. That makes sense, and maybe make both of those y. Some people use L and W for length and width. So, perimeter. What's a perimeter?
All sides added up.
Good, good. All right, it says all the sides added up. So if we added 2x plus 2y, they said that's supposed to come out to be 100, because peri means around. All right, area. How do you find area of a rectangle? Length times width. Okay, so x times y equals 300. Looks a little different than the other system that we had. But it's still a system, right? So maybe we try some substitution. So first thing I have to do is figure out which of these would give me something nice that I would actually want to work with if I'm doing substitution. Because right here, you know, people go to that immediately. Well, if I divide it by x, I'll have y equals 300 over x. Well, then you have fractions right away. So let's investigate what's going on with 2x plus 2y equals 100. And using that for substitution. Well, if I move one of them over and I divide by 2, everything in that equation is still going to be divisible by 2. So this would be a really nice one that won't have any fractions in it for me if I go after that. So I think I'll just go ahead and subtract the 2y from both sides and divide everything by 2. So now I have something that doesn't have any fractions that I can use for x. Well, substitution works this way. We solve for one of the variables and then we substitute it into the equation we haven't done anything with yet. And that would be this one. So I'm going to put this x value right where x is. It's going to look like that. Well, it's definitely different than what we saw before, but we can distribute this y from the right-hand side. It's got a y squared, and it has a y and it has a number. Think back. How do you solve something that looks like that? We do have to factor it if we can. So let's move everything over to one side. And I like to keep my first term positive, so I'm going to go ahead and add the y squared and subtract the 50y. So here comes the fun part. Two numbers and multiply to 300, add to -50. How many numbers are there that are going to multiply nice integers to 300? It's quite a few, right? So my question would be, am I wasting my time by sitting here trying to find them?
Yes.
Maybe you're saying I'm wasting my time? How do you know I'm wasting my time?
I already saw it.
And it's not nice, right? Do you remember how we can check to see whether or not something's factorable? Discriminant, good. That has to come out to be a perfect square in order for this to be factorable. So it wouldn't take us long to punch something like that in. That I don't consider a waste of time here. We've got our b squared, which is negative 50. So we have our negative 50 squared. And we need that minus 4 times 1 times 300. 1,300. Doesn't seem like a perfect square. And it's not. So if we had sat there and come up with them, that would be great, but we would realize in the end, it's not going to happen. So factoring's not working. What do we try? Could do the quadratic formula, but what's my favorite going to be? Completing the square. Completing the square. So let's move the 300 over. Do you remember the little formula that's going to give us the c value in ax squared plus bx plus c? Negative 50 divided by 2 squared. Exactly. B over 2 squared. So we're going to add 625 to both sides, which isn't too bad over here. What goes in this spot? 25, exactly. That's what we had to square things for. We're getting there. Got to keep solving though. What's next? The square's been too long.
Yeah.
How do we get rid of this so we gain access? There you go. Square root both sides. What do you have to be careful of when you square root? Good. And the last step is just adding the 25. Whew. All right, so let's see what that is, huh? 25 plus square root of 25. So y is approximately 43.028. And then I'll just cheat and hit second entry and go back and make this subtraction. Looks like so. Done? Uh-oh. What else do we need to do? There's x's that we have to find. So now we'll go back and say, okay, what would be the easiest way for us to figure out that x? Well, we knew we could just divide 300 by whatever we had here to get it. But we also have this really nice 50 minus y. So in order to keep this perfect, that would probably be the easiest one to do. 50 minus 25 plus the square root of 325, and 50 minus 25 minus the square root of 325. And that's because we don't want any rounding errors. We want to have it exact. So, minus 5 plus the square root of 325. So this one would give me an x value of approximately 6.972. Okay, that seems familiar. You see it? Okay, so what do you suppose is going to happen when we put the 6.972? So now we need to answer the question. And the question was, find the dimensions of a rectangular garden. Well, those are our dimensions. We just need a label. What was the label, Emma?
Feet.
Feet. So we've got 6.972 feet by 43.028 feet. Oh, I suppose I better not shorthand that one if I didn't do it the first time. There we go. So we've got another way to find that. We could find it graphically. You know, we could solve them both for y and then put them into the graphing calculator and see that we have the right answer. We already talked about algebraically. Go back and make sure that they work in both of them. But we had to do a little bit of rounding here. So if we went back and checked them algebraically, we might be off just a little teeny bit as we do that. So now, that was substitution. On to the next portion here that we're supposed to be able to do for our objective, which would be, you know, we're trying to see by graphing how are these solved. In example 2, we did not round the values found for x until we computed the values for y. For the sake of accuracy, do not round in intermediate results. So here's the deal. Back here, some of you might have been thinking, Cedar Home, you already had these in decimal form. So why not, there we go. Why not just plop it in here in decimal form? Because this is an intermediate result. I'm not finished yet. And if I round here, when I round again to get my final answer, I might have a rounding error. So we try to keep that as exact as we can all the way through the problem. And that's what they're saying here. Carry all your decimal places on your calculator computations. Just round your final answer so that you have things as exact as possible. This one says we're going to solve a nonlinear system algebraically. Ooh, look at that. I think we did that in Algebra 2 with the graphing calculator. We didn't necessarily do the algebra with you. So it says solve this system. Y equals x cubed minus 6x and y equals 3x. Perfect for substitution. They just told us y is 3x. So I can take this 3x and I can put it right there. Okay, but now I've got a cube and I have an x that's not going anywhere. Well, if I'm supposed to solve, I'm supposed to have zeros, so let me move this 3x over by subtraction, and maybe something will come to me about how I'm supposed to get the answers. Do you see something that would make sense to do at this point? What is it? Yeah, let's factor out an x. Oh, now that looks familiar. Can we factor x squared minus 9? Ow. Good. It says right away, x plus 3x minus 3. We've got that difference of 2 squares going right away. Not finished yet, though. We wanted the solutions. So everywhere there's an x, there's an answer. What's our answer for this one? 0. This one?
-3.
And this one. Now are we done? We want exactly, we need to find the line. So we go back up and think, well, which of these two little equations would be the easiest one to substitute in to get that? And the bottom one is just so quick and easy. All you do is take your x times 3. So 0 times 3, they're going to hit each other at 0, 0. -3 times 3 is -9. And then 3 times 3 is 9. So it should hit in 3 distinct spots, and there they are. Now, visually, we've just got this here for you because this is -5 by 5, so it is going by 1s this way, but it's going by 5s when you have those intervals for the y-axis because it's -15 by 15. We can see, okay, right there, it's 0, 0. They're going to hit. And then 1, 2, 3, and up, well, 5, 10, not quite to 10, it's 9. And if we wanted to, we could put this in our graphing calculator as y sub 1 and y sub 2 and let Blinky do the work on where those intersections are. So if we can't find it algebraically, we have a backup plan. Or if it's so complicated that we don't want to go ahead and do it algebraically, then we can also use the graphing calculator for those. So, solving systems graphically. That picture just connected what we had algebraically to the graphic part. In example 1, we graphed the 2 equations to verify our algebraic solution. There may be times that solving a system graphically may be the best way to solve the relationship. So, moving to that second objective a little bit deeper. y equals the natural log of x. How many of you right now, in the air in front of you, could draw me the graph, natural log of x, without grabbing your calculator? Draw it for me if you do, if you remember natural log of x, what it looks like. Okay, so some people are remembering that curve, that arc, but it's been a while. And what would we do if we set this up algebraically? It's y equals natural log of x. We'd substitute natural log of x equals this. Oh my goodness, now what? You know, so we've got natural log in with a quadratic. Easiest way to do this one is just going to be able to see where those intersections are. So number one says draw the graphs of the two equations, and they're giving us a window here. So is anybody going to need to borrow a calculator today? I haven't had a need for them for a while, so I thought maybe somebody might forget. All right, let's take a peek. The natural log of x. Natural log is just to the left of the 4. And then we need x squared minus 4x plus 2. And for those people that were gone, I probably better do this. Squared is 4x plus 2. All right. Window. They have a specific setting, and obviously they're not going to give us these settings all the time, but this is nice to start us off. Our x's they want from 0 to 10. Take the 0. Just after this morning, I was telling Mrs. Peterson how this one works so much nicer and how it's difficult. It won't take it. There it goes. Oh, I'm sure you already have this part in then. The y is from -5 to 5. All right, graph away. So there's our natural log of x, which again, we know, even though it looks like it stops, that's graph or error. It does continue on in the negative y direction forever. Two very obvious intersections, right? Been a while since we did this. How do we get Blinky to pop up and tell us what we need? Second trace. Which one are we looking at?
5.
5, good. And I'm just going to move Blinky a little bit closer to that first intersection to make sure that, hey, he knows that I say that's the one I want. So that would be the first one that we write down, right there. And that would be about 0.712 and 0.340. And there is a negative, isn't there? Teeny little negative right there, negative 0.340. And then the other one, second trace. And number 5 again. But get Blinky in the vicinity of the other intersection. Closer. There we go. And enter, enter, enter. So that one, 3.828, 1.342. So those would be our two intersections. Now, 3 says, use your knowledge about the graphs of logarithmic and quadratic functions to explain why this system has exactly 2 solutions. Isn't it possible that this red graph is somehow going to come back down? Why not? It's a parabola. Quadratics are parabolic. We can already see this is going to have that end behavior of up and up, positive infinity and positive infinity. Any chance that that natural log of x is gonna swing back and hit one of those quadratics? None. So what we know about their behavior tells us this is it. We know we don't have to look for any more. We have the intersections that we need. So we are viewing the only two possibilities that we have here. So that's what we would want to write down in our notes packet. So let's see, our intersections were 0.702, negative 0.340, and then we had 3.828, and 1.40, 1.342. Good thing I put the glasses on. There we go. And like we said, we are viewing the only possible solutions. Given what we know, about quadratics and natural law. That's it. We know that. We know we're done. So we look at them individually and say, all right, this one is supposed to be parabolic, gonna open up. This one has a nice arch to it, but it's not gonna swing back and it's not gonna hit what we need. So we know we have it. So that was the second part of our objective. And now we have another one here. It says solving a nonlinear system graphically. So why don't you go ahead and do that, and I'll put it up here and we'll see if we end up with the same solution or solutions. Just by spying on the first couple of people, I see you expanding your what you're doing is you're zooming in on that portion of the graph. Wondering, does it hit one spot? Does it hit in two spots? Some of you are getting closer and closer. How many spots? Intersection. Just one. Where is it? 1, 0. That's it. Just 1, 0. And it's really hard to make it out until, remember we've done zoom box before too? That would be another really good one to get closer in here and take another look at it. I'm wondering how difficult it's going to be on this big one to do zoom box. Yeah, it's going to take a while. I'm going to give up here. It's just taking way too long. Now that upper right corner is, or upper left corner is in the right spot anyway. But I saw it. one row that I went down. People are definitely working on that Zoom to see if we can get it. So, do we know that that's the only solution by what we saw and what we have for equations? Any way that one of them could start coming back and wrap itself around and bring us another solution? Nope, that's it. That's it. So we've got our substitution objective, we've got our graphing objective done. What else is there? Well, there's elimination. So the method of elimination, to solve by elimination, what we do is we make either the x's or y's opposites of each other, and then we add the equations together so that one of those variables drops out. Logan, stay with us. So this one says rewrite the two equations as two equivalent equations so that one of the variables has opposite coefficients. Then we add the two equations to eliminate that variable. So, could we use substitution with this? Absolutely, we could. We're going to have fractions as you deal with it. Most people don't necessarily like having fractions all the way through the problem. It could be we'll get fraction answers, but we don't want to have to work with them if we don't have to. So we take a look at this and we say, all right, let's see. The x's are not opposites. I could get them to be opposites. I could get this one to be a positive 6x and this one to be a negative 6x. I could go after the y's, 3 and 5. What would be our smallest number we want to work with for 3 and 5? 15. So we could make one of them negative 15 and the other one positive 15. But 15 is a bigger number than 6. So why not just multiply the top one by 3 and the bottom one by 2 and hope things work out nice? So we'd have 6x plus 9y equals 15. And then we'd have negative 6x plus 10y equals 42. Good news is we have our opposites. Add those two together, 6x plus negative 6x, the x's are gone. 19y equals 57. 19 going to 57 nicely. Yes. How many times? 3. Perfectly 3 times. Done! Now, what's left? Put it back in. And this is where substitution, you do most of the work up front, and then at the end it's really easy to get the second answer. With this one, it takes a little more work to get the second answer. I kind of like the top equation. It doesn't matter which one you use. So we'd have 2x plus 9 equals 5. 2x would equal negative 4, and x would equal negative 2. And then how do we round up this answer and get it so that people know we know exactly what we're doing? Ordered pair. Certainly wouldn't hurt to check it in the other equation too. But at this point, that's what we need to be able to do. That was another piece to the objective. So finding no solution. Wait a minute. They might not hit each other? Of course. Or they both cancel out in the algebra. Exactly. So that's what we want to see. Now obviously we've got the graph over here, so we know those two lines are, what are they called when they don't hit? Parallel. Yeah, they're parallel, but what if we didn't notice that? You know, sometimes you just get into the groove of doing the problems and you don't notice the obvious stuff. What would you do to solve this system? Divide the bottom one by 2. Multiply this one? No. This one. Okay? And so you're going after the x's? Or are you going after the y's? Doesn't make any difference, right? So let's multiply by 2 and get 2x minus 6y equals negative 4. Well, that's going to be 2x minus 6y negative 4.
Negative 2.
Thank you. There we go. To get them to be opposites. What's going to happen? So if they cancel out. No. Exactly. Somebody said all of them cancel out. They don't all cancel out, do they? What does that mean? No solutions. Now, if it were 0 equals 0, then what would we say? And I think Art had mentioned that one 0 equals 0. So this one would be no solutions, because we don't get the 0 equals 0. We got 0 equals something. You know, that's when we put no solutions down. All right. Graphing the equations on your graphing calculator in the same window can help us find the number of solutions in a system of 2 linear equations and 2 variables. 3 possibilities. We just saw one. They never hit. They're parallel, right? What's another possibility? They intersect. We get a solution. So what's the third one? Infinitely many. Exactly. And it just happens to be a line on top of itself when we do that. So they intersect at that single point. That gives us one solution. These are usually problems on the ACTs that have to do with always, sometimes, or never. You know, they'll ask you how many times can they intersect. The 2 lines can be parallel. No solution or infinitely many. And that's just a line back on top of itself. And they'll give you a couple of equations and say, do these always, sometimes, or never intersect? And you just need to figure out, is there a solution? If there is it just one, or is it infinitely many? So finding infinitely many solutions, what is your thoughts on this one? What would you like to do to this one? Top 1 by 3? Left side? Is it 0 this time? It is 0. Okay, so infinitely many solutions. So it's always true. If the statement is always true, infinitely many solutions. One of the other books talks about it as the identity. So some of you may have learned to write down the identity when you get to this point in the assignment, but that's going to be elimination. So now, oh good gravy, we're not going to have time to do linear regression. All right, so what I'm going to have to do is record. This one has us do linear regression on each of these sets of data, get the lines, and then see where they intersect. And we've done that before. And then the supply and demand curves, I'll also put that on video so that you can get that. But what you're going to want to do is write down both of the, well, better talk about this one more time. You already told me substitution was fine. Give me your 43210 on graphing and elimination. Okay, looking pretty good, looking pretty good. Lots of 3s and 4s, that's good. So let me see if I can scoop that one up on the bottom. And this will be on the notes on Schoology also.